Another problem for which exact solution of Navier-Stokes equations is available is what we call as equivalent layer problem. So we define the equivalent layer problem by considering a body of fluid on a surface when the surface is rotating at a constant angular velocity. So this is a problem that is in which we introduce rotation, and such thing in real conditions are available. For example, Earth, it is, as we all know, Earth is rotating all the time, and then there is a free air available which is affected by temperature, pressure and other weather conditions, and that generates a kind of a flow which affects our life. And also so this is a problem that is of interest to scientists and researchers, and that is why we consider it. We consider the surface to be almost flat and the fluid to have a horizontal free surface. On the free surface, we introduce a rectangular coordinates x, y, z. X and y are along the free surface, while the z is measured positively in the vertical upward direction. So the upward direction is considered to be positive, and that means that if we go below the origin in the downward vertical direction, that will be considered as negative movement in that direction. Let the free surface be subjected to a constant shearing force described by mu into S. H will be force, while mu is the coefficient of viscosity of the fluid that is flowing above the free surface. And this is the surface is acting along the x direction. Now, since the motion is considered to be steady, the velocity distribution is to be taken as u that depends on z, v that depends on z, and while there is no movement in the vertical or downward direction, so all the movement of the fluid flow that is taking place is along the xy plane. Now further, by absorbing the centripetal and the body forces, a modified pressure, we define it as P, in which we take the atmospheric pressure plus rho into chi, where chi absorbs the gravitational forces or the what we call as body forces, minus half rho into omega square r square. Omega is obviously the angular velocity of the body or of the fluid, and the chi is the body force potential given by F is equal to minus gradient of chi, and r is the perpendicular distance of a point from the axis of rotation. So we need to describe the problem very well in order to obtain the solution of the Navier-Stokes equation for this particular fluid flow problem. And this is important to describe all the parameters, so that when we obtain a solution, we can interpret it accordingly and properly. Now, since the velocity distribution is a function of z only, we will have the pressure derivatives with respect to x or y equal to 0. That will imply that dp by dx is 0 and dp partial derivative of p with respect to y is 0. So the partial derivative of p with respect to z will be non-zero. And the governing equations from the momentum components of Navier-Stokes equation will reduce to, with these assumptions that we have taken, will reduce to minus 2 omega 3 into nu equals to into v is equal to nu into d2u by dz2. And so I repeat this one again, minus 2 omega 3 into v, the velocity component v, is equal to nu into This is nu, the kinematic viscosity, which is equal to mu over rho. And this is equal to, so nu into d2u by dz2 and minus 2 omega 3 into u, the velocity component in the x direction, equals to nu the kinematic viscosity, times d2v by dz2. So these are the equations that we will have after deriving from the momentum components, momentum equation components of Navier-Stokes equation. The pressure gradient in the z direction is balanced by the Coriolis force. So the pressure, the force and the application of the pressure is to be balanced by the forces that are affected by the rotation. And hence from there we will have 2 times omega 1 into v minus, to write it more clearly, I would write it as this, minus omega 2 into u equals minus 1 over rho dp by dz. Now we note that omega 3 can be expressed as omega into cos of theta, and where theta is the angle between the vector omega and the unit vector k that is acting along the z coordinates, that is in the vertical direction. The solution of the coupled equations can be obtained in a very simple manner by multiplying the second equation by iota, where iota is the imaginary number described as iota equals square root of minus 1, and adding the two equations. We do this to obtain the solution in a simplistic manner. Thus the equation we can write as lambda equals to, if we take lambda to be the velocity components u plus iota into the velocity components v, and such that let alpha be taken as alpha squares equal to 2 iota into omega 3 by v. This will give us from the above equations another equation that is in the form d2 lambda over dz2 minus alpha square lambda equal to 0. And as we can see that the solution of this is pretty simple, and the boundary conditions will reduce to lambda at minus infinity is equal to 0. The acceptable solution is equal to lambda is equal to a raised some arbitrary constants into e to power minus e to power alpha z. As we can see from here, the two lambda will have the roots alpha and minus alpha. So I write it in the form lambda is equal to a into e to power alpha z, and a sign will take care of itself when we substitute into the equation, and therefore the values of lambda and k can be given as this quantity. That means alpha is equal to k plus 1 plus iota, and k is equal to omega 3 over v under root. Now using the condition at the free surface, where of course at the free surface the vertical component z is equal to 0 and mu into dtu by dz is equal to the shear force omega mu into s, and mu into dv by dz is equal to 0. So we obtain from this the constants a to be equal to 1 minus iota divided by 2k, and this gives us u is equal to the first part of the solution e to the this constant term into e to the power kz into cosine of kz minus pi by 4, and the velocity component v to be equal to s over k into 2 pi. You can substitute these equations and see and satisfy yourself that the equations are identically satisfied. The important features of the Ekman's problems are that the model equations exhibit a balance of viscous forces and Coriolis forces as mentioned earlier, and at the free surface where z is equal to 0, the velocity vector is u is equal to s over 2k into I minus j, and at a depth of pi over k, the velocity vector is given by this identity. I and j here are unit vectors. Thus, at a depth of pi over k, the velocity vector has decreased by a factor of e to pi minus phi, as can be seen from here, and its direction has become opposite to that of at the free surface. The depth pi over k can be quantified as this quantity. It is a measure of the Ekman layer thickness. The higher it is, the thicker is the Ekman layer, and note that omega 3 is equal to omega into cos theta. So the quantified quantities are as given.